One sort of flavor that you find the more and more you hang around category theorists is that they care a lot about relationships. So one way that you can study a thing or a mathematical object is kind of by taking a magnifying glass and looking at it from a very detailed close-up perspective, like kind of studying its internal anatomy. Another way you can study an object is by zooming out and seeing how it relates to all other objects sort of in its ambient environment. Category theory does the latter. So category theory places a premium on how one thing relates to another thing. And those relationships are usually drawn by pictures. This is such a fingerprint of this field that there is a theorem that says two mathematical objects, and I'll say what that is in a little bit, are the same, isomorphic, if and only if the network of ways they relate to other objects are the same, in a sense. So this is very sort of loose, and I'll get back to that theorem later. But it's not just a gut feeling that category theorists have. You can actually prove this formally, that this is a valuable thing to study. So what do I mean by objects? What are these things in these arrows? So for example, the objects could just be sets, and a relationship between two sets is just a function. Now, I'm going to make a very elementary observation, but it'll be useful, and you'll see why in a second. If I have two functions where the target of one matches the source of the other, I can compose them and get a third function. Okay. These blobs could be sets with extra structure. They could have linear structure on them, so I actually have vector spaces, Euclidean space to say. In this case, a relationship between two vector spaces is a function that preserves the structure that's there, i.e. a linear transformation. Again, I'm going to make a very simple observation. If I have two linear transformations where the source of one matches the target of the other, I can compose them and get a third linear map. What else could these blobs be? They could be sets, they could be vector spaces. We mentioned, probabilities earlier. These could even just be numbers, real numbers. Let's just say in between 0 and 1. What's a relationship between two numbers? Well, there's a very familiar one, which is the usual ordering. And again, I have this elementary observation that transitivity is sort of like this compositionality that I saw earlier. Okay, so maybe you're starting to seeing the pattern now. I'm just going to give you one more example of something else that fits this pattern. I could also have strings of symbols where a relationship now is substring containment. That defines actually a partial order, and so by transitivity, I have this composition again. If curiosity sits inside curiosity killed, which sits inside curiosity killed the cat, then I know curiosity sits inside the longer expression. So I've just given you 4 examples of categories without showing you the definition, but I think abstracting the examples, you can kind of see the definition now. Okay, loosely speaking, a category, call it C, consists of some objects, X, Y, Z, whatever. They could be sets or vector spaces or numbers or strings or etc. Together with, you have to specify a relationship or an arrow between them. So technically those are called morphisms. Together with a composition rule. So if there's a way to go from X to Y and a way to go from Y to Z, then you can combine those ways to get a way to go from X to Z. So some composition rule. And then you ask that this information satisfies some reasonable axioms that I won't get into. But this is sort of the data you need to have a category. And we just saw some examples. What does this have to do with language? So let me put up a little dictionary now so you can start to see the parallel. I mean, we saw it already, but I kind of want to hammer this point home. In category theory, you're interested in objects. I'm just going to say the word object to mean sets or vector spaces or topological spaces, whatever. Of course, in language, we have strings. In category theory, we're interested in all of the relationships between any given pair of objects. So I could have many ways to go from X to Y. If these are sets, right, there could be many functions from X to Y. Actually, it's important there that I wrote set. If you were to open your favorite textbook on category theory and you look at the formal definition, you will find that you ask for a set's worth of morphisms from X to Y, meaning there is a set of arrows from X to Y. The word set is really important. It's a set. It's not just some like, oh, there's stuff that goes from X to Y, but you actually ask that that collection be a set. In language, we also have a set. There is a set containing one arrow from blue to blueberry, and that arrow sort of witnesses the fact that blue is a substring of the phrase blueberry, okay? Well, on the left-hand side, there's a much more concise way to denote that set. So usually people will write C, which is the name of the ambient category of X comma Y. So C of X comma Y denotes the set of all morphisms or arrows from X to Y. Remember that because it'll come up later. In language, going back to the right-hand side, you can have something similar. You have something like a number, which I'm going to call pi, of blueberry given blue. Let's just think of this as something like the conditional probability that if I say or see the word blue, what's going to come after it is berry or avocado or ocean or whatever.
Was the pun intended? You said the pie of blueberry.
The conditional wait, what?
You said the pie of blueberry.
The pie of, yeah.
Was it an intended pun?
It was not. Oh. Oh, that's pretty good.
Because I'm hungry.
Well, listen, I'm on West Coast time, so it's like 6:30 a.m. right now. So yeah, it would be nice to have a blueberry pie. In this case, the pie, I mean as like the Greek letter, not the food, unfortunately. No, that's pretty good. I didn't think of that. Thank you. I should have been, yes, that was intended. Yeah, that was good. The conditional probability that I'm going to see something like berry given the word blue. I'm going to say something like and put that in air quotes because I'm not going to tell you like what do I mean by that? Where do you get those probabilities? But for now, just kind of view it as a placeholder. Yeah.
For language as well, can there be a whole set of morphisms and we're focusing on this particular?
Okay. Great question. Great question. In this setting, there is, because I'm defining the morphism to be substring containment, it's really binary. Like, does this string sit inside of this other string? Yes or no. If yes, there is an arrow. If no, there's no arrow and there's no other options. That's not to say someone else couldn't come up with another notion of relationship that's maybe useful. So I'm kind of giving us a category to work with, but that doesn't mean that there may be other ways to do it. In this case, there's only at most one arrow. But maybe we could think if there's other ways to do it. In which case you're working with a different category, which could be fine. But for here, at most one arrow in this talk. Yeah. Okay, so more generally then, just like on the left in category theory, you have this set of ways to go from X to Y denoted by C. And when we're thinking of language modeling, we have something that kind of looks similar. You have a probability of some string given some other string. Continuing to fill in my dictionary here. On the left, remember to have a category, I said you have to have some composition rule. So if you have a way to, this is just kind of the nice math way to write this. If you have a way to go from X to Y and a way to go from Y to Z, then you can compose them to get from X to Z. So if language fits nicely with category theory, then I would like for there to be some analogous composition rule, but in terms of these conditional probabilities of extending a string. And the question is there something here? In other words, let me phrase it like this. Category theory is this existing toolbox that has been around since the 40s. And I want to know, hey, do the tools that these mathematicians have been using, can I sort of repurpose them or like plug and chug in this context of language and see if I can get something useful? And the answer is yes, actually. And that's what I want to describe for you. So for the rest of the talk, I'm going to be kind of building up to filling in this question mark. And then seeing like, so what? So what? You fill in the question mark and then what? So I also want to tell you the so what of that. But let me just recap so far. Okay, before you even get to probabilities, you have something interesting. Language defines a category already. we already saw this. Our objects are strings from some finite token set or set of symbols. A relationship corresponds to substring containment and arrows composed by transitivity. Okay. You may say, so we know if this thing sits inside of this other thing, like what does that buy you? Well, it turns out there's actually a lot you can do with this. Okay, so we finished the first 2 points, and now I'm going to move on to the third one. Here are lots of things you can do with this so far. It seems like you haven't done much. I'm going to show you now there's a way that you can take this sort of bare bones category, even before you get to probabilities. There's a way to represent something like the meaning of a string, and I'm going to explain what that means. I'm going to then describe a way to operate on these meaning representations. Then we'll incorporate probabilities. That's point number 3. Once you do that, there's a way that you can repeat steps 1 and 2. You can represent meanings in this sort of statistical sense, and then you can operate on those representations. And then you can move to a geometric perspective and then use tools that kind of come from geometry. So this is all starting from, hey, does blue sit inside a blueberry? And what's the pi of that? Okay, what do I mean represent meanings? So this goes back to the picture that I mentioned earlier. Remember I said in category theory, there's a theorem that says 2 mathematical objects are isomorphic, or the same. There's a formal definition of isomorphism, but they're the same if and only if the ways they relate to ambient objects in the category are the same. So this is, to me, sort of like the mathematical analog of the distributional hypothesis in linguistics. So there's this idea that 2 words have similar meanings if they appear in similar contexts. Or there's this famous quote by linguist John Firth, "You shall know a word by the company it keeps." So like, what's a dog? We'll look at all the other strings that contain the word dog, and that tells you something about it. So the point is, actually, this is how mathematicians think of mathematical objects as well. So you can also see the parallel between category theory and language from that perspective. I actually want to show you that theorem that I just mentioned in slightly more formal notation, because we're going to use that notation repeatedly. So let me describe this idea a little more formally. Pick an object X. Like imagine X is this object in the middle here. Maybe this is a set or a vector space or a string. Now, remember, C of X comma Y is the set of all relationships from X to Y, right? So if I remove Y and I just leave it blank, I just have the totality of all ways that X relates to every other object. In particular, if I fix an object in the category and plug it in, I get a set. So if I fix X, I choose another object, I get a set. So by thinking about how objects relate to one another, I've just described for you a relationship, a way to go from the category C to actually the category of sets. We saw that as an example. There is a category whose objects are sets and the relationships are functions. So this idea, a way to go from one category to another, it's called a functor. So functors are relationships from categories. So this C of X comma blank, this says, okay, if you give me some object like Y, I plug it in and I get a set out. So given Y, I output the set of all relationships from X to Y. A functor, I'm not going to give you the formal definition, but it's a mapping on categories that also respects the composition rule between arrows. And so the theorem that I mentioned, it's actually called the Yoneda lemma. This is category theory's most famous theorem. Like if you've never heard of category theory, probably you've heard of someone say the Yoneda lemma at some point, if you rub shoulders with him. But the theorem states that 2 objects, X and Y, are isomorphic. So that's a formal definition. I won't give it to you, but they're essentially the same if and only if the functors that represent them are the same. And these functors are exactly, it's that picture, like the network of all relationships associated to a given object. These functors are actually called representable because they sort of represent the essence of the object. So this is how category theorists think. They say, look, you can study X Or you can study the functor that represents X, i.e. you could study all of the relationships that are sort of associated with X, and that gives you everything you need to know as well. In the context of language, though, here's how this translates. Given some prompt or expression, little x, we want to consider the network of ways it fits into that category of strings, which we're calling capital L. And just to recap, what that means is we say, okay, given a string like blue and some other string like curiosity killed the cat, I just want to know, does blue sit in that string, yes or no? If yes, there's an arrow. If no, there's no arrow. So for example, a string, instead of studying the string itself, I want to study the functor representing that string. What is this thing? This is a set. It only looks like two possible sets. The set contains the singleton arrow if blue contains that string I'm evaluating it on, like blueberry, or it's the empty set if when I evaluate this function on a string that does not contain the word blue. Does that kind of make sense? Okay, if it doesn't, here's a better way I like to think of this functor. This functor is basically like a binary vector indexed by all possible strings from your alphabet. And it's like a 0, 1 vector. There's a 0 if that string does not contain the word you're interested in, and it's a 1 otherwise. But, 0 is actually the empty set. And this asterisk is just like the set with 1 point in it. Does that make sense? So I kind of like to think of these functors, these sort of vector-looking things associated with strings, kind of like the one-hot encodings of category theory, not just because they're binary valued, but actually there's a precise way to see this. There could be other, mappings from my category of strings to set that don't look like this. Maybe there's more complicated ones. Turns out there's a theorem. Those more complicated ones are built up from these sort of representable ones. So there's a real sense, kind of like you have a vector space and you have basis vectors, and linear combinations give you more interesting things. These are like the basis vectors in a sense. So sort of like one-hot encodings associated to words. This is more interesting than the string of letters B-L-U-E. Yeah.
So there is someone having
Oh,
a question.
Sure.
If you can unmute the
Yeah, so-
Okay.
and,
Okay. I have unmuted the laptop. If you're on Google Meet.
Yes.
Good. We can hear you.
Great. So I see how this gives like a binary notion of meaning of the two objects are exactly the same. Does category theory provide kind of a more continuous notion of sameness versus differentness, or do you just have to kind of like, that's up to you to put some kind of distance metric yourself?
Okay, thank you for that question. I'm gonna mute, but if you have further questions, just ask. I want to make sure that the sound is okay. Okay, in this case, great observation. The Yoneda lemma basically says two strings are the same if and only if they are the same, because it's binary, so there's not much wiggle room. So in that sense, I want to think of the Yoneda lemma as more like motivation to consider this functor, as opposed to it telling me something new that I didn't already know, if that answers your question. There is sort of an enriched version of the Yoneda lemma, which gives a little bit more information, and I'll get to that later. I think that maybe by the end of the talk, you'll see that this sort of two things are the same if and only if their functors are, is more of like a launching point for more interesting structures that can maybe give an answer in a better way than just this beginning. So for right now, that's not giving us something totally new, but now that we've moved to functors, there's richer information there. That's how I'm going to answer that now, but it's a good question. If there's other questions on the chat, maybe Tom, you can let me know. Yeah, in the audience. Yes.
I guess it's the one. And the unit that yeah. So to me, this feels almost like a definition of equivalence. I think that the reason maybe is because we don't have the definition for
Yeah,
right?
exactly.
So could you try to give some sense of what what it means to be equivalent?
Sure. Yeah. So if you're on Zoom and didn't hear, is this last line the definition of this isomorphic symbol or what? No. So no. If X and Y are sets, then to be the same, I just mean there's a bijection between them. If X and Y are vector spaces, I just mean there's a linear isomorphism between them. If they're topological spaces, I mean that there's a homeomorphism between them.
Could you
So-
explain like the unit lemma for linear vector space?
Yes. So if X and Y are vector spaces, then let's just say finite dimensional for simplicity. X and Y to be isomorphic, they're going to have the same dimension, right? I mean, this is like the only thing that's really interesting. So what that means is that, okay, now it's a little bit hard because I have to tell you what does it mean for two functors to be isomorphic, but I didn't tell you what a functor is. Right, but here, let me say it this way. Imagine you plug in any other vector space into the empty part, okay, like some other vector space Z. What this now is asking for is a bijection between two sets. So that means that the number of linear transformations from X to Z must be equal to the number of linear transformations from Y to Z. And if that is true for every space Z, then I know that X and Y must have the same dimension. Yeah, perfect. I know. So there's multiple layers you kind of have. That's why I didn't tell you definitions. But yeah, it's good. So just to recap, don't take this as the definition of what it means to be the same, but it's like if I have some notion of things, then I can make this statement. Yeah, thank you. Thank you for that. Great. Okay, so what's the advantage then of moving from strings to sort of their functors that represent them, or these vectors, right? Number one, this functor captures something of the context of my string that I'm interested in, right? It's telling me everything that contains it, which according, in the spirit of this distributional hypothesis from linguistics, right, which is an idea from the 50s, that tells you something of the meaning of this word. Here's how people use this word in this language. That tells us something about it. Number one, that's one advantage. Number two, notice you can't really do any operations on strings. Remember our category. It just says, oh, this string goes with this other one. But what about, like notions of conjunction or disjunction or negation? What about the fact that I can concatenate strings? Like there's no structure there. It's just saying yes or no, does this fit inside? So that's what I mean. It doesn't feel like you've done much. But now when you pass, instead of looking at strings, you look at sort of these vectors representing them, you have much more structure now. Think of it like this. If you have a set of 3 elements, you can't do anything with it, A, B, C. If you look at real valued functions on that set, you're now working with essentially a vector space of dimension 3. Because you can add real numbers, you can add vectors together. Just do it component-wise. You can scalar multiply vectors component-wise. You have all of this structure because the reals have structure. Similarly, a string, there's not much you can do with it. But now that I am dealing with sets, you can do a lot of things with sets. I know how to take intersections of sets. I know how to take unions, products, a whole bunch of stuff. So we have more structure at our disposal and we can start to combine things. Now here's why this is interesting, not just because it's useful maybe to think about, does this match with things in linguistics that people care about? But these operations fit very nicely into things category theorists already do. So quite often in mathematics, you may have a bunch of stuff, vector spaces, sets, whatever, and you say, okay, given this collection, what are some ways that I can build new things from them? If you have vector spaces, maybe you take their, Cartesian product, direct sum, whatever you want. Like, how do I get a new vector space from existing ones? If you look across the mathematical landscape and you look at all of the ways that you can sort of construct things, it turns out they really fall into two, I was going to say categories, but like 2 buckets, okay? And they have formal definitions, which I'm not going to show you, but in category theory, there's sort of 2 ways to construct new things, and they're dual of one another. On the one hand, you have a construction that's called a limit. On the other, it's called a colimit. The names don't matter. The interesting thing is that many things we're familiar with are special cases of these categorical constructions. For example, intersections of sets, products of groups or vector spaces, direct sums, meets in a lattice, even greatest common divisors of integers. These are all special cases of a single definition of some concept called a limit in category theory. Dual to that, in a very precise notion of duality, you get other things that people were familiar with, like unions of sets. Co-products are like disjoint unions. Direct sums, again, joins in a lattice, least common multiples. Turns out these are all special cases of this more general concept called a co-limit. There's a question.
You have direct sums and both limits and co-limits.
Yes, they turn out to be the same in some cases.
Okay.
So,
And is this kind of like first of all, theorem and group theory, or the relationship between the dimension of the kernel?
yeah, that's what I mean. Yep, the direct sum in that sense. Yes.
Divided by the.
Yeah. Yeah. So in the first isomorphism theorem, I do mean direct sum in that sense. When I'm talking about greatest and least common multiples, I actually mean like in the kindergarten version.
Like the relationship between limit and co-limit seems to be kind of similar in your.
Oh, yeah.
One is divided by the other, and you get the original object.
It's a little bit different than that, actually. Maybe there's a way to see that they're related, but what I mean in terms of duality, just the following. You have some category and there's arrows, and you make a definition and you get a limit. If you just turn the arrows in the other direction, you get this other thing called a co-limit. That's kind of the sense in which they're related to one another. Yeah.
Sometimes words are not contained. There's not a relationship of being contained in, but it's implicit. For example, if I say the color of this wall reminds me of the one of this. So is there a way through those factors to find or some function between this and this sentence that reminds me a lot? Blue is in implicit.
Okay, that's such a good question. I don't know. What I'm describing for you today is like level 1 in a larger program. And maybe your question is like, you will come back and tell us the answer one day after I give you these tools. I'm not sure yet, because now we're thinking about concepts and how things are sort of abstractly related to one another. I think maybe by the end of this talk, you'll see I'm going to describe for you a category theory in which maybe like concepts or concept hierarchies form. And then maybe there's a way to connect them. But this is entry level right here. I'm not sure yet. We haven't gotten to that level yet. And in fact, I don't have a good idea even to speculate, which I think you'll see maybe why in a second. I'm going to show you on the next slide what we can do, which is maybe tools that could be used to ask questions like that. But yeah.
It's just like, I'm sorry, it's just like for me, there's this duality between the structure of the thing and the meaning itself.
Yeah.
And I'm wondering if those factors, what do they express really? Is that like a structural or a syntax thing or a semantic relation?
Yeah, okay. So I think there is a way in which these functors we're describing now are semantic. They contain semantic information in the sense of this sort of linguistic distributional hypothesis sense. The question you're asking is very good, actually, but I don't know that this framework yet is equipped to address it. But I think maybe these tools, I think the point I want to show you today is there's something interesting here that's maybe worth looking at for that reason. So let me show you what we can do, and then we can maybe see, is this plausible, or is maybe there are other category theoretical ideas that are better suited for that. So here's what we can do. When those blobs on this screen, when these are these functors associated to words, as I was saying, the outputs of these functors, when you evaluate them on a string, you get a set. So that's nice because we know how to build new sets from old sets. We can take intersections, products, unions, and so forth. So it turns out if I take this existing definition of something like a co-limit, this very abstract thing that I didn't show you, and I plug it into our language category, I can take something that's like the disjunction between the meaning of the word red and the meaning of the word blue, for example. In category theory, the formal phrase is you take the co-product of co-sheaves. co-presheaves. It doesn't matter what that is. I'm just telling you, there's like, you open a book, there's a definition. When you plug that definition into our language setting, you get, well, if I apply this operation to the functor for red and the functor for blue, I'm going to get another functor. So it's going to look again like a vector indexed by strings. And here's what you get. This vector is empty, or I will say this vector is non-empty, like it has a 1 or non-zero number on the union of strings that contain red or blue or both. And then you get an empty set or a 0 otherwise. So this functor is sort of supported on the union of all strings that contain red or blue or both. So that pairs nicely with the sort of role that union plays as logical or among sets. Now there's a construction for the product or conjunction, and you can even talk about implication. It gets a little more complicated there, so I'm not going to show you that one. But the point is, you could, in our original category, you can't ask, like, what does it mean to have a cat and a dog, just with strings. But when you pass to sort of these functors that represent the strings, now you have interesting structure that you're inheriting from sets. And this sort of gives you some logical operations that you can start to think, oh, maybe I can see how concepts are maybe combined. Turns out there's more interesting stuff you can do, which I'm going to say on the last slide, that's maybe getting closer to what you're asking about. But I'm just trying to give you evidence. There's stuff here. Okay, this is all before we said anything about statistics, right? So maybe what you'd really like, sure, this is nice, but maybe what you really would like to work with is a vector that has actually not just does this string sit in this one, yes or no, but something like these conditional probabilities of containment. So maybe instead of just having an arrow that blue sits inside of blueberry, witnessing that containment, I want something like, yes, but that arrow is also decorated with something like this conditional probability, right? The nice thing is we don't have to do this ad hoc. So there's already existing framework in the literature that this fits perfectly into. So this is something called enriched category theory. So I'm going to introduce it as follows. Remember, in category theory, each pair of objects has a set associated to it, a set of all ways to go from X to Y. Quite often in math, this set may not just be a set. Imagine X and Y are vector spaces. Then these arrows are linear maps. Well, if I have two linear maps, I can add them and get another linear map. I can scalar multiply, get another linear. So my set actually is itself a vector space, right? Like if I pick bases for X and Y, these arrows are just matrices, and you can add matrices of the same size. You can scalar multiply them. So you have a vector space worth of matrices. So you don't just have a set, you have some other mathematical object. It's a vector space or something else in some sufficiently nice category. The point for us is that an example of a nice category is precisely the unit interval, numbers between 0 and 1 that we saw at the very beginning. And that's good because that's all we want to see here. So I was saying, hey, wouldn't it be nice if we could just kind of label arrows with numbers? And what I'm trying to tell you is there's already framework in category theory that folks have been using for other purposes. And it just turns out that statistics from language fit perfectly into these existing notions, which have been used in pure math, like exclusively. So I think that's pretty cool. There is a definition, I'm not going to go through this, but there is a definition of an enriched category, just like there was of a regular category. The point is, in our case, this amounts to a collection of strings, X, Y, Z, and so forth, and these numbers. So instead of, a set from X to Y, I have something like a number from X to Y, which I'm going to think of like the conditional probability of seeing X as an output given like prompt or input. Sorry, Y as an output given a prompt or input X. The thing is, for this setup to fit into this sort of concept of enriched category theory, remember the composition rule given a way to go from here to here and a way to go from here to here, there's a way to combine them. In this setting, what that amounts to is having this inequality. So if we can choose these sort of conditional probabilities, which I keep putting in air quotes because I haven't said what they are, but if we can find some numbers that satisfy this inequality, the way to go from X to Y times the way to go from Y to Z is less than or equal to the way to go from X to Z. Then we can say, oh yes, language does fit nicely into this enriched categorical framework. So how should we choose the pi then? Well, it turns out this is exactly what happens if you have an autoregressive language model, or let's just say a large language model. So for any prompt, if you have an LLM, right, it gives you a probability distribution on this token set. And these probabilities multiply in the sense that if I feed in a prompt X1, I get a probability distribution, which I'll describe as P, of whatever given X1, and I sample from that. Let's say I sample another token X2, I feed that in, I get a probability distribution on the token set. So the probability of my full string given my initial input is just the product of the successive probabilities along the way. So in general, if you think of a long string as being obtained by sampling it one token at a time, and you do that with a language model, I can think of defining these pi's from these probabilities on token sets. So if I have some string, let's say, my string is big blue ocean. So I'm going to think of the probability of ocean given a string, or let's say big blue given a string, an initial string, as the product of the successive probabilities of getting that one token at a time. So that's what my pi of xy are. If my x and y are equal, just define it to be 1. And if x is not a subset of y, a substring of y, just define it to be 0. When you make this definition, then you can check. You get exactly this inequality that you wanted. So the point is, if I define these probabilities of substring containment as that generated by a language model, this allows us to view strings as a category enriched over this unit interval. Okay, so who cares? Well, number 1, that means I can fill in my nice dictionary from earlier. So maybe that is a clue that there's something to this. And it turns out there is. So remember how we were able to kind of get these binary valued vectors representing strings and we could operate on them? It turns out you can do the same thing with enriched category theory. So in this sort of category theory 2.0, there are definitions of enriched functors and enriched limits and co-limits that already exist. So when you specialize to our case, it turns out, I won't go through the definition, but I'll kind of tell you the punchline. You have what are called enriched co-precies or enriched functors. And you get exactly, in this sort of statistical setting, I have a functor associated to a string. And when I unwind the definition, I get exactly this vector indexed by strings before, but now my entries are precisely these conditional probabilities. So remember I said you could have just done that in an ad hoc way maybe and see what you get. But the point is, this already exists in the literature. And when you specialize to our setting, it fits perfectly in that. And then I mentioned there's ways to do things like conjunction or disjunction or even implication in enriched category theory. So again, if you open up your favorite textbook, they have these sort of complicated definitions called weighted limits and co-limits. In our setting, if I take sort of the disjunction between the functor for red and blue, again, I get a vector indexed by strings. But now the entries, if you look at the mathematical structure and sort of the definitions, these numbers now are going to be the maximum of the numbers I get by associating each individual functor on a string. So you plug in each functor and you see which one is larger, and then that's what ends up in the vector. The upshot, though, it's supported on the union of texts that contain either red or blue or both. So it's again fitting with this idea of or. Okay, I want to close with something that's more recent, which I think is pretty cool. So probabilities are nice. There's things you can do with it. You can talk about meanings. You can talk about some logical operations. But there's a way that you can also have a geometric perspective. So what you can do is think of now applying negative log to each of your probabilities. So instead of having a number between 0 and 1, I'm going to get a number between 0 and infinity included. What this allows me to do now is instead of thinking of a string labeled by a probability, I now think of distances between strings. And under this, strings that are likely continuations of other strings are close by. And those that are not contained at all are infinitely far away. So I have something like a metric space now of words, and a sentence is like a path in this space. It's not just like a metric space. Actually, this D satisfies the triangle inequality. Satisfies the triangle inequality, which in fact turns out to be exactly what you need to have this composition rule in category theory. So this is well studied by category theorists. Categories enriched over 0 to infinity are called generalized metric spaces. They don't satisfy symmetry. So the distance from x to y is not necessarily the distance from y to x, but you don't just toss it out. You still get something interesting, a generalized metric space. And the point is, you do the whole story over again. You can talk about meaning representations from this geometric perspective. You can, again, combine those meaning representations in this geometric perspective. What else can you do? So here's some work by myself and Juan Pablo Vigneault, who's at Caltech. It turns out that there's really interesting connections now to topology and information theory when you think of this. So there's a notion called magnitude. Magnitude is something, actually it's really interesting. It started in sort of investigations of biological diversity, like how diverse is my ecosystem in this particular setting. And a category theorist, Tom Leinster, took that notion and applied it to category theory several years ago. This is a number associated to a generalized metric space, which sort of captures an effective size. It's a little bit different than volume and area, but it generalizes those notions in ways. This notion of magnitude also generalizes the concept of Euler characteristic in topology. So if you're familiar with that, it's sort of counting how many faces and vertices and edges that you might have. So this generalizes that. So we take this idea and apply it to our metric space of language. So you have, language is like all of these strings, and a sentence is like a path in this string in this space. You want to know, like, what's the effective size of this linguistic space from this categorical perspective, and you get a number. So I'm not gonna go through that number, but here's how you think of it. I'm gonna think of two extremes, and I'm gonna close on this point. If you have a deterministic language model, just think a language model that's programmed to just give you like a preferred string, like hello world, hello world, hello world. No matter what you feed in, this is all it gives. There's not much room for exploration, right? So I'm imagining my space is like this tree. At every node, I can go, each sort of leaf in this tree is like a different token that I can sample from. So if I say there's only one path in this tree, I compute the magnitude. It's this number. I get something relatively small. It doesn't really matter what it is, so I'm not going to describe the notation, but something that's smaller than the magnitude I get for a random language model. So let's say a random language model is one where every string is equally likely. Okay, so my path of exploration is ginormous. Like at every prompt, any token is equally likely as any other. So you can see in this formula for magnitude, you have a sum of h sub t of p of x. These are Salas entropies. So if x is a prompt, I get a probability distribution over the token set. I can take the Salas entropy of that distribution. I add them all up. I scale by some factor, and then here's another number. Let me not worry about this. But it's interesting that entropy is popping up in this calculation, because in a sense, it's like measuring, okay, at each next step, how uncertain is the model for where it should go next. In the deterministic case, there's no uncertainty, so the magnitude is relatively small. In the random case, there's maximal uncertainty, and so you get a larger number. Okay, then other language models fall somewhere in between those two extremes. So that's why I like to think of, roughly speaking, this number that we get is sort of capturing something like the effective size of this linguistic space. Again, I want to emphasize, magnitude is a concept that category theorists have been studying. It came out of like biological diversity, but to be able to apply this in the context of language is giving maybe a new way to think about how to characterize language models, how to think about numerical or other kinds of invariants that capture something unique about a particular language. So these are interesting categorical tools that are arising. But there's other things you can do, and I'll close here. So to kind of answer your question, like what else can we do with this? What do we have other questions that we want to ask? So it turns out there's, I don't know if anyone here is familiar with formal concept analysis. So these are ways to build sort of concept hierarchies using ideas from lattice theory. It turns out that's a special construction of something in category theory. And so we've explored that in a paper that came out last year. There's a group with John Torilla and others that have found connections to linear logic and distributional type theory. So this is interesting. They take a slightly different approach. Our original category just looked at what strings fit inside of which other strings. But we totally ignored the fact that you can take two strings and concatenate them together, like hot dog. So what happens if you have this sort of multiplicative structure? Well, it turns out you get nice connections to logic here. Also, Samantha Jarvis is a recent PhD graduate from CUNY, and so she investigated sort of how does that multiplicative monoidal structure, how does that behave when you pass to these functors? So now can you start to talk about logic also with this idea of concatenating strings? So there's interesting math theory there. And then again, if you say, well, this is all nice for theory, but can we do something interesting with this? So there was actually a group at the Amazon AI Labs last year that did some benchmark tests using semantic representations inspired by these functor representations. So sort of thinking of the meaning of a string, not just as a word embedding, but sort of capturing like all of the, paths that could be continued by that string from this perspective. And so they got some good results. And so that paper is pretty interesting too. Okay, I know I'm at time and that was a lot. So I think I'll end here and thank you for your attention. Okay.
Thanks, Lene, for the presentation. Now we'll start the question phase. Okay. And then you go first. Well, in the live, and then you can pass it around.
Sure.
Thank you for an amazing and really insightful talk. That was super cool. I just wanted to kind of double check an intuition and see if that was predicted correctly by category theory or not. With regards to like the notion of equivalence or sameness.
Yeah.
Maybe like an intuition I would have is that red and blue, as far as strings go, they're the same in that you can kind of switch them across sentences and the meaning of those sentences would roughly be the same. The specific notion of like a substring morphism that we were talking about, would that capture that notion of sameness? I have a feeling it's no, not yet, but is there some way of composing together these representations to get that sense that like, red and blue kind of play the same role?
Yeah, that's a great question. In the framework that I just described for you, no, not really. It's a little bit too rigid, and I think that relates to maybe a question that we had on the meet, on the chat. However, this on the upper right-hand corner, I think is a little bit more helpful in answering this, in the sense that red and blue are the kind of the same in that they're both instantiations of the concept of color. So they're used interchangeably in that sense. So then you want to know, okay, but what's the concept of a color as opposed to the concept of a house pet or something else? This paper on the upper left makes the connection in the following way. So just think about singular value decomposition for a second. You have some information and maybe it's in a large space and you want to compress it into a smaller dimensional space where you actually have meanings or something interesting, and this is where word embeddings come from. There's an analogous construction and category theory, which takes these large functors, okay, which are indexed by all strings, which is a lot, but it kind of compresses it down to a smaller category, which maybe takes out the extraneous information. And I think there's room to see, oh, in this space, there's like a subspace, which is like where red and blue and yellow live or something. And there you can kind of see that they're more closely maybe clustered together than something like cat and dog or something else. There's hope that this direction is where that would lie for reasons that it relates. I mean, the analog to linear algebra is like so close, it's not coincidental. So I think there's room for it there. We haven't gotten there yet. I mean, this is kind of also where Samantha's paper is coming in. But in what I've shown for you now, no, but I think it's a clue that there's other directions within this framework to look. So thank you.
Very cool.
That was a good question. Yeah, other questions?
Let me give you the mic.
All right, I have two questions. Maybe I'll ask one and there's remaining time. There's this notion of universal grammar of Noam Chomsky. This is something that quite fascinated me. And you talked about topology, and we're talking about invariance in topology. And I was wondering if I would see this universal grammar notion, just to tell people what it is. It's the fact that we're born with the anatomic structure that fits, that makes us more prone to language. It was a criticism of Skinner, who was a behaviorist of the 60s and 70s, and said that we can acquire language just through teaching in environment. And I was wondering, I'm coming to my question, I was wondering if through category theory, you could find some invariants that are independent from the context.
Okay, good question. In this framework, I would say no, because I'm more looking at how language is used versus how it's developed in the mind. However, do you know the work of Matilda Marcoli? Okay, so she is a mathematician at Caltech who recently just wrote a book with Chomsky. Actually, it came out recently, where she is looking at ideas from mathematical physics, actually, and the merge operations. It's interesting because she also has ideas in category theory where maybe they can take a similar enriched categorical approach from that Chomsky perspective and maybe compare it to the magnitude, for example, of the category you get here. So, but that's outside of my area of expertise, so I don't have an answer for that, other than I do know that people are thinking about these things and that the tools are kind of there for the taking. We've had interesting conversations, but that's not a project that I'm working on. This is more like how is language used, sort of, you know, in a corpora of text. But I think these ideas, it's so general that it can easily be applied as long as you get your right, you know, category. What are your strings? What are your morphisms? It's doable. I think it's work in progress. So maybe keep an eye out and see what happens. That's a good question. Thank you.
You're welcome. If there's no other question, I can ask that.
Hi, thanks for the talk. Sorry, I should really apologize for only coming in 5 minutes ago, but I did listen to your talk mostly online. I had another meeting
no
I had to run away from.
No problem.
Yeah, my question is, I've seen Disco Cat
yeah.
framework before, and I wanted to ask, is this like a completely different framework, or is it like a direct like map from one or the other?
Oh, good question.
Yeah, and in particular, like here you have these enriched categories, but I don't remember exactly how Disco Cat works, but I think it was a symmetric monodal closed category.
Yeah.
So I just wanted to like learn a bit about the
Yeah,
relationship.
excellent. Thank you for that question. This is very different in the fact You notice I have no grammatical input here whatsoever. So in DiscoCat, I think the sort of key idea there is you're sort of tagging your strings or your words with different grammar, like pre-group grammar or something, and then composing them. Here, we're taking a different approach. Language models, you don't have to give them grammatical input. And so we're asking a different question. What is that mathematical structure there? How can you produce these coherent strings of text only given knowledge of which strings go with which other strings with their statistics? So I think maybe that's like the easiest way to see the difference, which is that there's no grammar here. Certainly there are ideas of category theory, but you'll notice here, I don't have any sort of, I'm not imposing any structure on my category. I don't have to ask that it be symmetric, monodal, compact, closed, or anything. And that, maybe if you saw at the first slide, if you were on the Google Meet, that was the point I wanted to make. We brought very few assumptions. In fact, like no assumptions, other than, this string goes with this, yes or no, and what's the probability. And from there, you get a lot. So that's kind of why I like this framework in particular, is because you don't have to make a lot of assumptions about, does your data have certain property? If so, then you can say this. It's kind of like, well, let's just see what we have and how far we can get. Yeah, thank you for that.
Thanks.
Oh, behind you.
Okay, thank you for the presentation. My question is related to how model learn representation of language. For example, today, it's known that if you take, for example, a group and train a model to learn that group, model and transformer try to learn the representation of that group before generalizing. So they try to learn the group. But on text, it's not clear what representation of text is. Because, but I'm wondering if by moving from language to something called category, and define the representation of text that says and try to see model try to learn.
Yeah. So actually, I think that's what this paper on the bottom left is attempting to do. So this is not a group that I was involved with, but Stefano Soato is the head of the AI lab, and Matthew Traeger is, I think, one of the leads on this paper. So they're exactly taking this idea. Maybe a representation of some text is, sure you have word embeddings, but they're taking this perspective. Maybe it is something like, I think instead of using the word functor, they look at like equivalence classes for some notion of equivalence for all strings that contain a particular word. And then they do, I think, semantic similarity benchmark tests on that, and they got good results. I would recommend you just look up the name Matthew Traeger and Stefano Soato. They have a very nice blog post on the Amazon AI blogs, where they describe all of this, I think, from a high level perspective, and then you can read the archive paper. But I think they're motivated by this sort of categorical perspective, and it turned out to work very well. In fact, they presented their work at ICLR, and so I should keep in touch and see how that went. But yeah, there's room for that. I think there's people that are investigating that. Thank you for that question. Yeah. Other questions? We have one up in the middle.
Thanks a lot for the talk. One slide I found particularly interesting is the one with the continuum from a fully deterministic model to a fully random model and everything in between. There's a lot of research interest now in assessing the confidence of a language model, in particular in detecting cases of possible hallucinations. Do you believe that this enhanced category theory could be used to measure the likelihood of hallucinations overall, or maybe to find out if for a particular prompt the model is deep in the woods and it should probably say, I don't know?
I appreciate that. I would hope so. There is a small problem, though, which is actually, even though this is true, these numbers are huge, actually. So for example, ob of m, these are basically all possible strings that you can form from your token set. So just think of like your tokens and look at the free monoid on it. This lower number here is the number of all possible outputs from the model. So given the beginning of sentence token, either your output could go to the cutoff length of your model or until it reaches the end of sentence token. So this is a huge number. And then to compute this, you need to compute the Salas entropy over every possible input. So I think computationally, to just try to like run an experiment on this would not work so well because it's so large. I think it would be nice to think about ways that you can actually make this more computationally feasible so that you can run some experiments on real models. Right now, we're encouraged by the theory of it. And I mean, there's even ways to associate this number to subspaces of your model. So like you can put in one string and then look at the magnitude of the sort of metric space of possibilities from that one prompt. So maybe if that prompt you see your model tends to hallucinate a lot, maybe the magnitude is larger there, and maybe that can be useful. This is hot off the press though, so this work was just accepted recently for publication, and we're making some edits on it now. But my hope is that the more we get this out there, and maybe there are collaborations that can form. I like that this is a new tool that maybe can be used for assessment, and I'm hoping that it can be used for things like this. Maybe if we think about a little bit better about how to deal with it computationally.
Thanks a lot.
Thank you for that. Okay.
Any more question? More question?
Oh, one more question.
My beloved supervisor asked maybe the same question. Actually, he talked about symmetrical monoidal category, and I was wondering if you could have a concrete example where you could see what's the tensor composition in language and the sequential one.
Oh. Well, I would have to, the sequential composition could just be substring containment, and maybe the tensor product could just be concatenation. I mean, I would need to sit down and write that out and check that it satisfies all the axioms, but sequential composition could be like the usual thing, but maybe if I have two strings, I can think of the sort of tensor product as like, you know, if I have blue ocean, red dog, I can concatenate somehow. I don't know. I need to think about it more. And I don't remember how it's done in DiscoCat, but I don't know. I need to think offline about that.
Thank you.
Yeah, putting me on the spot. Thanks.
No, I'm sorry.
Good. Okay.
Great. Well, then if there is a question, then thanks again one last time.
Thank you. Thanks.